This is the inefficient way. And so at this point right here, the body has to make a decision. So you can imagine you're running a marathon. And let's say that you don't run very often. Okay? So you're out there running a marathon, and you're about mile 2, mile 3, physically exhausted, not truly muscle fatigue, because remember, muscle fatigue occurs at the level of the muscle, not your head. And at this point, what's happening? Well, your body is telling your muscles to run, but they're not receiving enough oxygen. Right? So your body's telling it to run, you're still going to provide ATP. But at this point, you're not going to be able to take that pyruvic acid and go over there and produce it efficiently. Instead, what you're going to start to do is produce lactic acid. And it's going to start building up in your muscles. And so the very next day, after running your marathon, and hopefully you're finished, you're going to wake up and not be able to move because you're going to be so sore. And that can actually lead to very serious problems. You can actually die from lactic acidosis if you didn't know that. Okay. You ever seen A Few Good Men? That's how he died in that movie. Okay. So, lactic acid will build up, not necessarily a good thing. Now, if you become better at exercising, you become more efficient, then you can learn to use glucose a little bit better, which is why if you exercise on a routine basis, you don't get sore as often. Because you're able to use the glucose more efficiently, break it down, and build up plenty of ATP. Does that make sense? So I want you to understand the general idea. So we're going to talk about how is ATP regenerated. So we have 3 ways. ATP is regenerated by creatine phosphate. It is regenerated by the anaerobic pathway, which I would call glycolysis. But if you want to write anaerobic pathway, I'm fine with that. But glycolysis is really the name of that. Glycolysis. Do you want me to write that down? Or is it your notes? Okay, that's what I thought. And then the last one is called the aerobic pathway, which is actually a combination of what we call the Krebs cycle and oxidative phosphorylation, which you don't need to know that. But that requires oxygen, though. Both the Krebs cycle and oxidative phosphorylation require it. We can talk about that during the break if you want to know why. It's not critical for this discussion. We talked about muscle fatigue. I say it right here again. Muscle fatigue, a state of physiological inability to contract, even though the muscle is still receiving stimuli. So again, this is at the level of the muscle. It's not your brain saying, stop moving muscles, I'm done. It's the muscle is receiving stimuli and it doesn't move. It doesn't contract. There's a difference. Okay? There's a lot of different reasons why that can happen. And you can read about these here. But this is how you get cramps, contractures, and other things can happen in your body. It's all due to really muscle fatigue. Various different things. Buildup of energy or ion imbalances and various other things like that. The nice thing about it is if you work out more and more and more, the more you use your muscles, the more efficient you get at using them. And guess what? You won't cramp as much. You won't get lactic acid buildup as much. And again, it just goes to show you why you should exercise more and more. This idea of oxygen debt on page 21 is just real simple. I'm not probably ever even asking you about this, but it just makes sense. So if you go back to the muscle, right? In its resting state, it's got glycogen in it, right? You got that polymer of glucose. It has a small amount of ATP ready to go. It's got a small amount of creatine phosphate ready to go, right? Well, if you just ran and used that muscle, you've depleted all the supplies. So now you need to build up the supplies again. That is an oxygen debt. You need to pay back what you've used. That's all they're talking about here. And that requires oxygen to get it all built back up. Okay? So that's what oxygen debt's all about. It's just building back, replenishing the creatine phosphate, the glucose, the glycogen, and everything else. Getting rid of lactic acid, getting that out of the muscle, getting back to a standard resting state. Heat production. If I don't, again, I would never specifically ask you something about this, but if I don't tell you that muscles make heat, when you get to 102, they're going to be like, you never heard muscles make heat? The major way by which your body is warmed up is by muscle activity. The reason why you can maintain body temperature of 98.6 degrees Fahrenheit, 37 degrees Celsius, is by your muscle activity. Right? Muscles produce heat. They're inefficient at using energy. And inefficiency leads to heat loss. Which is why when you exercise, you get hot and you have to sweat to compensate, right? That's what that whole negative feedback mechanism is. And also if you're cold, I went camping on Friday night because I'm crazy and dumb. Because I have 2 kids in Cub Scouts who were crazy and dumb. And trust me, when we're all standing by the fire, we're all going like this. Because we know that when you move your muscles, right, you're going to warm up. So the kids are running around, you know, keeping all warm. They were actually hot. They're taking off clothes. It's 27 degrees outside. They're taking off clothes. All the guys around the fire. Right? But moving muscles is going to build up heat. Okay. So don't forget that. Heat production occurs during muscle activity. Okay. This is just a simple little picture showing the last thing here. So force and muscle contraction, we talked about the basic idea of all this already. Okay? If you think about a muscle, right? If you have a muscle that has a lot of muscle fibers, a lot of muscle cells, that's going to be a stronger muscle than one that has less number of cells, right? So if you have a muscle that has 100 fibers versus a muscle that has 1,000 fibers, the muscle with 1,000 fibers is going to be stronger. Right? That's all we're saying. Okay? The number of muscle fibers increases with the muscle contraction strength or tension. Relative size of the muscle and muscle fibers. So we talked about this as well, hypertrophy. People think that working out makes their muscles bigger, and they're right, but it doesn't increase the number of muscle fibers. It increases the size of those muscle fibers. They get bigger. Okay? So as you increase your muscles and you do what's called anaerobic activities, so not running, okay, not endurance, but rather conditioning, say lifting weights, it's going to build up the muscle size from the fiber size. It's going to get bigger and bigger and bigger. And that's what makes the muscle stronger. Yes.
Because they get more myofibrils, though?
They do. They do, yeah. They get more of everything, really. They just grow in size overall. Frequency of stimulation. We talked about that. That as you increase the frequency of stimuli, you increase the force of the muscle contraction. And then the last thing here is just the degree of muscle stretch. And this is somewhat easy to visualize, again, if you think about your muscle here, right? So we have a state right here where you can probably imagine that right here, this condition of being stretched is probably the maximum. The maximal strength right in this position. If I put it in this position, I'm not quite as strong. If I put it over here, I'm not quite as strong. So there's a condition or a state in which the muscle is in perfect relaxed state to get the maximum resistance or the maximum pull. And that's basically what it's showing right here. So there's an optimum resting strength, and at this point, you get the maximum pulling potential. That's all. Going back to what Polly asked earlier about muscle fibers. We talked very simply about muscles having muscle fibers, but what we did not talk about is that there's different types of fibers. So you can imagine that there's some fibers that are very, very fast to respond. We call those fast twitch. So they contract very rapidly, and they relax very rapidly. Fast twitch. Whereas we have some that are slow twitch. They are slow to contract, slow to relax. And so again, you go back to that very early picture we had of the eye muscles versus the muscles in the calf. And the reason why those muscles are different is because of the muscle fibers they have. The muscle fibers in the ocular muscle are fast twitch. The fibers in the calf are more slow twitch. And that's all it is. Okay? Going just one step further, we also can get ATP from different ways. And I said before that glycolysis, or the anaerobic pathway, I made it seem to you like that was a bad thing. And it is, from an efficiency point of view. But the body's not always about being efficient. The body's about getting things done. Right? And so we have situations where the body would rather be fast, even if it's an inefficient way of doing it, as opposed to being slow and being more energy efficient. So what I'm going here is we have something called glycolytic fibers. These fibers preferentially use glycolysis and end there because they want to be fast. Boom. They don't want to take all the time it takes to do the more efficient pathway. They want to just plow through the glucose, move on, move on, move on. So we have what's called fast glycolytic fibers. And then we have fibers that are more slow and oxidative. These guys are slow to respond, but highly efficient. These guys are the ones that you might find in endurance racers, right? You can imagine high endurance. You want to use very little energy to get it done. You don't care about getting across the finish line in a 100-meter dash in, what, 12 seconds, 10 seconds. You're worried about running 10, 12 miles and just getting to the end, right? So we can imagine we have different types of fibers. And I'm going to show you a real easy way to think about this, and I think this is the best way to show this. We have two different types of athletes. We have a marathon runner, and we have a sprinter. A sprinter and a marathon runner. Now a sprinter, if you look at the muscles in their legs, the majority of the muscle fibers are going to be fast and glycolytic. That means they're going to respond very, very fast, but they're going to tire out very, very fast. That's what they're going to be. Okay? So this person can run a 100-meter dash very, very fast. But you put that person running 5 miles, and they're not going to make it. They're not designed for that. Their muscles, by their own exercise regime, have been designed or changed to be mostly fast glycolytic. 63% of them. Whereas only 37% are slow and oxidative. They're not built for endurance, they're built for speed. Look at a marathon runner. Marathon runner fibers are mostly slow and oxidative, versus a very small number of fast and glycolytic. So again, just goes to show you the body can change. One of the, I've actually never said this before, but it kind of makes sense to say it now. Back in 1940 something, my grandfather was trying out for the Pan American Games. He was from Cuba. I didn't tell you I'm Cuban. He was in Pan American Games trying out for it, and Cuba has tons and tons of sprinters, but no one's ever run a mile. It just doesn't happen. So he went out to try out for the mile. It was the first time it was ever offered. He went out. So he's starting to run, and if you know, a mile is 4 times around the track, 1,600 meters. Okay. So he starts off, and everybody else sprints out like crazy. They're all sprinters. They're running 10, 12 seconds, 100-meter dashes, right? And they're, I mean, I don't know if they lapped him, but it wouldn't surprise me if they lapped him. But slow and steady wins the race. He went to the Pan American Games that year. Because everybody else, well, he would have. Everybody else died before they got to the end of the finish line. World War II happened. It never happened. But the point is that, again, those sprinters were designed for running very, very fast, but they didn't have the endurance. So they slowed down. They couldn't keep up. Right? Slow and steady wins the race. It's like a turtle, right? So that's what we're talking about with marathon runners and sprinters and jumpers. Anything else? Yeah, I'm going to talk about that. I'm going to talk about recruitment. We talked about this already before, right? When you think about motor units, or again, the same way I think about moving the piano. If you want to move something heavy, if you want to move the load, you have to recruit more and more muscle fibers. You do that with recruitment, right? So you're going to employ or recruit more and more and more. Does that make sense how you're going to do that? You can't, let's say motor unit 1 is not sufficient to move the piano. You have to employ motor unit 2 and 3 and 4 and 5 until the entire muscle is recruited, and then hopefully you can move the piano. That's what we're talking about with recruitment. That's really the key. Let's talk about the effects of exercise on muscles. Anything else to show you? Okay. The only thing I want to show you here is this idea of the overload principle. So circle that. It's already bolded for you there. Let's look at that. Overload principle. This is a very basic concept to anybody who either runs or anybody who weight lifts. All right? So you should understand this general idea, the overload principle. Let's say that you want to build muscle mass. You want to make your muscles stronger. And so you decide your biceps brachii, now you want to make these things big. You want to have big guns, right? So every single day, you take weight, a 20-pound weight, and you do 3 reps of 10 every day. And you notice over a short period of time that your biceps get bigger. But guess what? After a while, they don't get any bigger. You keep going every single day, and every single day you do the same thing. Every single day you do the same thing. They never get any bigger. You've maxed out. Why? overload principle. At a certain point, you have to go more. You have to go to 25, then 30, 35 to 40. The only way your muscle is going to get bigger is by overloading it. Same thing's true with endurance. People say when you're starting to run a marathon, right? If you're starting to work up to a marathon, you start off running 20 minutes. Okay? 3 miles. If you're starting off, you've never run before. 3 miles. It's roughly 20
A mile and a
minutes.
half or something.
Well, whatever. Okay? Whatever it ends up being. So, run for 20 minutes, and then run for 25, then run for 30, then 35. Okay? And hopefully you're going to start building up. Every single week you increase it by 5 minutes. Or 1 mile. Whichever you want to do, okay? And so you're building up, you're building up, you're building up. People who run a Boston Marathon don't do it overnight. They build up, okay? And they get better and better and better by overloading themselves week in and week out. That's the way to do it. So with building muscle mass or building stamina, the way to do it is the overload principle. You have to increase the load all the time to increase the strength or stamina endurance. The only one. The last thing to talk about here, I'm going to make it real simple. We talked a lot today about skeletal muscle. We talked virtually nothing about cardiac muscle, and we're not going to. Okay, that's for one over here. I do want to mention very, very briefly about smooth muscle. And there's only a few things I want you to know. In other words, the majority of things that are here in bold, you don't need to know. Okay. You have to cover enough right now. What I'm really going to talk about is comparing and contrasting smooth muscle versus skeletal muscle. And I'll make it very clear what I expect you to know. Okay. Well, let's talk about what smooth muscle looks like. This is a picture of smooth muscle. That would be, for example, in the lumen. So food in your intestine would be in this area right here. Okay? That's actually the passageway for food. And here you can see muscle. Now if you look carefully, you're going to see that the muscle fibers are going this way, and the muscle fibers are going this way, kind of wrapping around the two. So they're going in opposite directions, here and this way. They're not weaved, but they're one layer on top of the other. Why is that? Well, it's this process called peristalsis. What is that exactly? Well, imagine I have a tube, and I want to move food. There's 2 ways to do it. Squeeze, and pull together, right? Squeeze and pull. Squeeze, squeeze. And to a rhythmic of doing that, I'm getting food being moved down the lumen. Squeezing, squeezing, moving like that. So we have this, I guess you call it circle muscle, and then you have a longitudinal muscle. And again, it's pulling together and squeezing, pulling together and squeezing. So that's the way those muscles are designed. So you can do peristalsis, or movement of the food down the intestinal tract. You even find this around large arteries. This maintains blood pressure. You actually can keep these muscles contracted, and that's actually what maintains blood pressure. Or relax the muscles and reduce blood pressure. You'll learn more about that in 102. Okay. Now, as far as what the muscles look like, let's go this picture. That's fine. When we have a skeletal muscle, we have a neuromuscular junction. It's a very defined area where the neuron attaches to the motor end plate. It's a specific place on the skeletal muscle that the neuron is going to attach to. When it comes to smooth muscle, it's not quite so precise. It's more diffuse. So you have what's called diffuse junctions. They're just kind of scattered around across numerous cells, and they form what's called diffuse junctions. And I can maybe show you a better picture than this. I thought I had a better one. No, I don't. It's okay. If you notice here, I'm not going to. There's a bunch of pictures back here that came from a different textbook that I think in many cases can help you understand the basic processes. But since it didn't come from your book, I didn't want to go through all that. So if you want to look online, you can look at that during the break. Okay, let me go back real quick. Okay. This is what the individual muscle cells look like for a smooth muscle. So they're not multinucleated, they're not long strands like you see with skeletal muscles. Rather, they're kind of short, I don't know what you want to call that shape of cell. And then what you have when you have the muscles contracting is the myofilaments that you have, actin, for example, that shortens. You actually have it kind of squished up like that. So all the muscle cells all squish in uniform, and the muscle shortens in that regard. So I have more pictures. That's good. All right. Let's talk about similarities. Okay. The similarities to skeletal muscle. So actin and myosin. We talked a lot about actin and myosin, or the thick and thin filaments. We have the same thing in smooth muscle. They're still thick and thin filaments. They're still made of actin and myosin. Actin is thin, myosin is thick. Same thing. The sliding filament mechanism, we talked about how actin and myosin pull on each other. Same kind of idea. They still pull on each other. Same kind of process. The final trigger is calcium. Yes, calcium going up in a smooth muscle causes contraction. Calcium levels going down ends contraction. Same trigger, same end. Dissimilarities. Look here on page 26, it says calmodulin. Circle that. Page 26, calmodulin. Remember we talked about the troponin and the tropomyosin complex? The troponin is what senses calcium, and then it moves tropomyosin away and exposes the active site. With smooth muscle, we don't have that. Instead, the sensor is calmodulin. That senses the level of calcium, and that leads to contraction of the muscle. There's a difference. So you don't have troponin, tropomyosin, instead you have calmodulin. That's one of the biggest, if not the biggest difference I would expect you to know. Some other things just to be aware of. Anything else I want to mention here? The other thing I mentioned is skeletal muscles. You saw how we have motor units, and one muscle cell gets activated, and only that muscle fiber gets activated, and no other fibers unless we specifically turn those on. That's how we get graded muscle responses, right? We can turn on one motor unit, but not the other, right? So we can go like this, or we can go like that, by activating different motor units. When it comes to smooth muscle, it's not quite that clear. And I wish they had a better picture than this. Hard to tell. Maybe I have it. Yeah, I do. Good. See right here? See how those muscle cells are connected? Those are gap junctions. Remember what gap junctions are? They allow things like calcium to travel between cell to cell. So you can imagine that if I increase the calcium level right here in this cell, that's going to diffuse into this cell, which will diffuse into that cell, that cell, that cell, that cell. It'll spread. And so what you end up having is waves of contraction that occur in smooth muscle. It's not a controlled, very specific, controlled contraction like it is with skeletal muscle. This is more a, let's start the ball rolling, and it just kind of has waves of contraction. Waves and waves and waves and waves. It's very low energy too. It's a very efficient way of getting contraction. It's slow to start, slow to stop, very efficient use of it. Why? Well, because the body doesn't want to spend a lot of time doing that kind of contraction. It wants to spend its major energy doing what you want it to do, moving. So it designed a very simple way of contraction for something like visceral muscle, moving foodstuffs. So it's very efficient use of ATP. That's all I want to say. There's some other things here you can see. I'm not going to get into stress relaxation response or plasticity or hyperplasia. You can read about that on your own. Your muscles can change as you grow up, as you enter puberty and things like that. You can read about it, but I don't want to get into that. And then the types of smooth muscle, I'm not going to get into that either. There's multi-unit versus single unit. It just gets too complicated. So I'm not going to ask anything about that, but if you want to read about it, any questions? Told you it would be somewhere between 7:30 and 8. I get it on the notes, so I've got about 10 minutes to 8. No? as I said, really try to understand the mechanisms. I don't know exactly how I'll ask questions, but I would expect you to understand certain aspects of muscle contraction. Like understanding key ideas like calcium. What's the role of calcium, right? Understanding the basic idea of an action potential. We're talking about propagating electrical impulse. I would not get detailed and expect you to understand that sodium first comes in and then potassium then comes out. That's too complicated at this point. We will come back to that again with chapter 11. So we'll come back. But for now, I would expect that level. All right. Let's go ahead.